In Chapter 2, we want to look at how are we going to deal with our data once we've collected it. So in Chapter 1, we talked all about how do you collect data, how do you take a sample, what types of studies are you going to do. So in Chapter 2, now you're sitting around with all this data you collected, so what do you do with it? So we want to talk a little bit about first how you're going to organize your data. So typically, before we go about actually organizing our data, we want to figure out what type of variables are we even working with. So typically, variables are broken down into two categories and really three categories. So the first distinction we make is between qualitative and quantitative data. Now, the difference between these two types of data is in the titles. So qualitative data describes qualities about objects, okay, whereas quantitative data describes quantities. So if I'm holding an apple in front of you, then I could make an observation about that apple, such as this apple is green. That's a qualitative observation. I could also tell you, hey, I put this apple on a scale and it weighs 0.53 pounds. That's a quantitative observation about the apple. Within quantitative, we also break down between what we call discrete and continuous. And I'm going to explain the difference between those in a few slides. Alright, so let's look a little more specifically and let's get a definition. So qualitative data, it consists of variables that describe characteristics about individuals that classify them into groups or categories. So sometimes this is also known as categorical data because it groups them into categories. So some examples of qualitative data. So we already saw the one, like the color of an apple. But some other examples include gender, your race, your ethnicity. Okay, so these are things about you that group you into categories but are not numerical. Okay, they're not quantities. If you're talking about plants, you could be observing their species or their color or the genome. Qualitative data is pretty much always non-numerical. That means not numbers. Okay, they can be numerical. So an exception to that rule would be like your zip code or your area code. Okay, so your zip code or your area code, all they do is they group you into a category. They tell me where you live, what city or what part of a city you live in, what state or what part of a state you live in based on your area code. Okay, so they don't have to be non-numerical, but typically qualitative data is non-numerical. Alright, so quantitative data, these are always numerical values, and they have to have some inherent ordering, meaning that lower numbers means you have less of it, and higher numbers mean you have more of it. So within quantitative data, though, we do split it apart into two groups. So the first we have is discrete quantitative data. So discrete quantitative data, these are variables that only occur on fixed intervals. And typically those intervals are integer values. So an example could be the number of family members in your household. Okay, so you can only claim on a tax return 1 or 2 or 3 or 4 or 5 or a fixed number of people in a household. I can't claim 4.75 children on my tax return. Okay, I have to pick an integer number. Another example could be, say, the number of eggs that are laid by a chicken. Okay, a chicken's going to lay none or 1 or 5 or 23 eggs. Okay, they can't lay half eggs or quarter eggs or 0.73 eggs, right? Discrete quantitative data is pretty much always on integers. It doesn't have to be necessarily. Like I could think maybe if you're talking about how much milk can you buy at the local grocery store. Well, if you walk into the grocery store, you can't just buy any amount of milk you want. You have to buy it in either pints or quarts or half gallons or gallons. Okay, so that's still a discrete quantitative random variable. Alright, so those are discrete, and then of course on the flip side of that we have what we call continuous quantitative data. So continuous data, these are variables that their values can occur on a continuum, and they can take on infinitely many values. So we're talking like when you think about decimals, okay, you can come up with infinitely many decimal values. Now in real life, we obviously round off our observations. So if I ask you how old you are, you're not going to tell me your age to the nearest millionth of a decimal place. You're just going to round it off to the nearest year. If you go to the store and want to buy something, they're going to round your price off to the nearest cent. But those types of variables like time, money, age, those are really what we consider continuous because they occur on a continuum. We just round them off for convenience. Now, if it's not really clear whether you have qualitative or quantitative data, I always ask myself this question. I say, would it make sense to average these values? So like, for example, does it make sense to average people's age? Yeah, that makes sense. That's a quantitative variable. Does it make sense to average people's zip codes? I would say it doesn't. I mean, I can't imagine what good it would do to average two zip codes. It's not like the average. If you take the zip code of, say, Pasco and the zip code of Seattle, it's not like if you average those two, you're going to come up with the zip code of Cle Elum, even though it's right in the middle of the two cities. Okay, so zip codes don't make any sense to average. They're not quantitative data. So if it makes sense to average it, then that's a good sign that you have quantitative data. Alright, so once you know what type of data you're actually dealing with, it's going to drive what type of graphs and summaries you should use to describe the data. So typically, when we are doing any amount of data analysis, the very first step you should take is to make a graph. So the most common graphs that we use for qualitative data are going to be frequency distributions, relative frequency distributions, bar charts, and then pie charts. So I want to talk about each of these a little bit. So a frequency distribution is basically a table. And it's a table on one column that lists all the possible values of your qualitative variable. And then on the other column, it lists how frequently that variable popped up in your sample. So let's look at an example. So here is a table, and it shows the frequency that each color popped up in a sample of 3 bags of M&Ms. So someone went out, bought 3 bags of M&M's candies, emptied them out, and counted how many of each color they observed. So they counted them up, and there was 152 brown M&Ms, 114 yellow M&Ms, 106 red, 51 orange, 43 green, 43 blue. I think they were doing this experiment because they liked blue M&Ms, and they were feeling really disappointed that they weren't getting a lot of blue M&Ms in their packages. So they wanted to see if it was true that there's less blues in a bag overall. Okay, so they wanted to see maybe they just got a really unlucky bag. Turns out it looks like that in general the blues do occur less often. Alright, so this is an example of a frequency distribution. It breaks down the categories and tells you how many are in each of those. Now, frequency distributions, they don't necessarily give us the most useful amount of information. So, for example, if I did the sample and you asked me, you said, "Hey, Ryan, how'd that M&M's experiment go?" And I'd be like, "Oh yeah, I did the experiment and I found 43 blue M&Ms." And you say, well, that's great, I guess, except for how many M&Ms did you sample, right? Because if I got 43 blue M&Ms and I had only sampled 100, that's a big difference than getting 43 blue M&Ms out of like 1,000, right? So one way we can summarize our data rather than frequency is in a relative frequency distribution. So in a relative frequency distribution, rather than listing the counts, like how frequently they popped up, you actually list the proportion or percentage of time that each category popped up. So if you look at our M&M's frequency distribution from the past slide, we can actually convert those counts into percentages. So if you look at what we have here, what I've done is, so the first 2 columns, the color and the frequency, that's just copied over from the previous frequency distribution. Now, if you add up the total number of M&Ms that were sampled, you're going to find that there were 509 M&Ms sampled. Okay, so if I want to figure out, okay, so there are 152 brown M&Ms, what portion of the total 509 does that take up? So what I do is I take 152 and divide it by the total, 509. That'll give me the decimal 0.299, which is 29.9%. So about 30% of the M&Ms were brown. For yellow, that would be 114 out of 509. That's 0.224, or a little over 22%. Red's 106 over 509. That's 0.208, or 20.8%. Orange is 51 out of 509. That's pretty much 10% dead on. And then 43 out of 509 for these last two. That's a little over 8%. Okay. Now, typically in a relative frequency distribution, we wouldn't include the original frequency and then the calculations. So on the next slide, I just simplified it and I just gave the relative frequency. These are just copied from the last slide. I just got rid of all the work in between. Now, relative frequency, you can show it using either the decimal or the percentage notation. Typically, like in explaining things to other people, we tend to use percentages because that's what we're familiar with. But just for displaying it, especially in math, we're totally happy just using the proportions. Okay, so either way though, I would accept it with percentages or proportions. I think on your homework, probably it's going to be looking for proportions, but just pay attention, the units would be specified. Alright, so frequency and relative frequency distributions, these are great, except for, some people think they're not really very pretty. Right, so they say, that's great, good information, but I want a nice, more graphical, pictorial representation of this data. So what we come up with then is ways to turn our frequency relative frequency distributions into a more pictorial representation. So the first way we can do that is we could make a bar chart. And what a bar chart is, it's a pictorial representation of the frequency distribution. And the way it's created is that a bar is drawn for each category, and the height of the bar corresponds with the frequency. And it's pretty straightforward. So if you look back to our original frequency distribution for the M&Ms, what I'm going to do is I'm going to take each of those categories and I'm going to draw a bar, and that bar is going to go up as high as the counts. All right, so here, so I'm going to skip forward here, and this is what it would look like. Okay, so the brown M&Ms, there was 152 of them, so there's a bar drawn up to 152. There was 114 yellow M&Ms, they drew a bar up to 114, and so on and so forth. Okay, so what the bar graph does is it gives us a nice picture that describes describes the frequency distribution. The advantage too is that it allows you to make quick comparisons. So rather than looking at a table and having to compare numbers, we can just look at these bars and we can compare these numbers, because it kind of sees like, brown is above and beyond. Yellow, red are similar, orange, green, and blue are similar. Okay, and it allows us to make those comparisons a lot quicker than trying to sift through numbers. All right, so that's the advantage of a bar chart. It also looks a lot nicer in a report. Kind of looks pretty. Give it colors and things like that. Right? That's a bar chart. And notice that the bars don't touch, and that actually becomes an important distinction. We'll see why in a moment. Alright, so maybe though you want to work with the relative frequency distribution, so one way we can turn those relative frequency distributions into a nice pictorial representation are with pie charts. And in this case you take a whole pie, you divide it into slices, and each slice takes up a portion of the pie that corresponds to its relative frequency. So you look at the example that we had for the M&Ms, right? If you look back at what we had, so browns took up, 8.4%? Or I'm sorry, blues took up 8.4%. So blue gets a slice of pie that takes up 8.4%. Brown had 152, that was 29.8%, 29.9%. So brown gets a slice of pie that takes up 29% of the pie. And so on. Red was 20%, so red gets a nice slice here that takes up 20.8% of the pie, right? So everybody gets a slice, and how big your slice is depends on what percent of the sample it took up. Alright, so those are the four main types. You got your frequency, relative frequency, those are tables, and then you can turn those into bar charts or pie charts. And those are typically the most common pictorial representations that you're going to see for qualitative data. Alright, so what if, instead though, we have quantitative data? So quantitative data is usually displayed by using a histogram. And what a histogram does is it displays the overall shape of a distribution, and it draws bars associated with data that fall in certain ranges. Okay, so to explain how to construct a histogram and have you kind of see how this works, I'll have you look at the chart on the next page. So what this is the unemployment rate for high school graduates over the course of like almost 15 years. I think it is 15 years, okay, plus a month. And so every single month the unemployment rate was recorded for the United States. And you can see there's just numbers everywhere. You can kind of see some big years and some low years, and then some bigger years and back to low years and things like that. Okay, so looking at this chart, it's kind of hard to make any sense of, what the unemployment rate was like at any given, at a sort of an overall trend. Okay, and you don't really want to have to make a frequency distribution or a bar chart for every single decimal point, right? So I'd have to go all the way down to like 3 point something and all the way up to 7 or 7.3, and this frequency distribution, you have all these categories and not very many months in any of those categories. So what we do instead is we basically establish some bins or classes. So I noticed that my unemployment rates ran generally from about 3% up to about 7.5%. So what I've done is I've split that range into equal sized bins. So each bin has a width of 0.5%. Okay, so like I said, okay, well, I'm going to group together everybody every month between 3 and 3.4%, and then I'm going to group together every month between 3.5 and 3.9%, and then the 4%, the 4% to 4.4, then 4.5, then 5, 5.5, and so on. And so what you do is you set these class widths, and typically what you want to try to do is you want to divide it up so that you end up with about 5 to 10 classes, 5 to 10 bins. Alright, so that's how I think here I ended up with what I got here, 9 maybe, 9 I think. Alright, and then what you do is you just go through your data and you count up how many months fell in each of these categories. Alright, so that's what I've done. So there were 9 months where the unemployment rate was between 3 and 3.4%. There was 2 months where it was above 7%. Okay, so I've counted them all up. Alright, so then once we have those bins established and we have counted up how many people go in there, the histogram is kind of like a bar chart. Okay, we're going to take a bar and we're going to make it as high as 9, and we're going to take a bar here and make it as high as 27. You can see that's what I've done here in the histogram. Alright, now the main difference between a bar chart and a histogram is that in a histogram the bars touch, and the bars touch for a reason. The bars touch, first of all, because this is a continuous random variable. When you go from the first bar to the second bar, these have to butt up to each other because this ends at 3.49 and picks up at 3.5 in the next bar. The other reason the bars touch in a histogram is you can't move these bars around. It wouldn't make any sense to take the 3 to 3.5% bar and plop it up here at the top and maybe move the 6 to 6.5 to the middle, and you can't move these bars around. Okay, they have to occur in this order. Whereas back at our bar chart, I'm going to scroll back, we're talking about M&Ms. Who cares if brown comes first? Maybe put brown at the end and blue at the beginning or whatever, or arrange them smallest to largest. Okay, doesn't matter for a bar chart. In a histogram, they have to come in order. Okay, they have to be in order, and the bars have to touch. But otherwise, it's pretty much like a bar chart. But it's what we use for quantitative data. Ooh, almost said the wrong one there. Quantitative data. All right. So that's a histogram for you, and that's pretty much the most common and really probably about the only plot you would need if you're just looking at one variable. That's quantitative. Okay, so the last thing we want to talk about is the fact that with those histograms, you can start to actually observe the overall shape of distributions. Some of the most common shapes that you're going to encounter and that we're going to deal with in this class are shapes like skewed and symmetric. Okay, so here, if you look back at the data we just did with the unemployment, you can kind of see that this data is a little bit skewed, right? It's like it's kind of all piled up down here between maybe 3 and 5.5%. And then it tapers off here. Some months happen up here, but not as common up here above like 5.5%. Okay, you can kind of get this overall shape going on. And if we look right here, this is actually an example of what we would call right skewed data. Okay, so if data is skewed, it means it's kind of all piled up in one section, but it kind of tapers off as you go towards one direction. So, and then the skewness is whichever way the sort of tail of the distribution is pulled. So right here you can see this thing kind of gets pulled up to the right, so we say it's right skewed. This one over here, this tail kind of gets pulled down to the left, we say that's left skewed. And then, of course, this one right here, this one is symmetric. Okay, so no big deal there. Obviously symmetric because it's the same on both sides. This distribution in the middle, This is also known as a bell-shaped distribution, okay, or maybe a normal distribution. We're going to use normal distribution most of the time in this class. Variables tend to follow one of these three, most of the variables we observe, although there's plenty of other distributions that could be the case. The ones we're going to deal with mostly in this class are going to be these three. Some examples here. So some examples of variables that could be right skewed. You could think probably incomes in America are very right skewed. Most of us are down here at the maybe $0 to $100,000 a year level. And then there are some people up here at very high incomes, but there's not very many. Okay, once you hit maybe $100,000, it starts to taper off very quickly. But there are some people up here, right? And there's obviously a lower bound here. You can't go below 0. Some maybe another one I can think is right skewed could be like maternal age, like the age of a woman when she gives birth. So most women are giving birth down here in the years between, say, 15 to maybe 40. And then some, plenty of people do give birth over 40, but it tapers off pretty quickly. And then there are those rare, older women who give birth maybe in their 60s. Okay. As far as symmetric goes, tons of data is symmetric. These are things like maybe the heights of people are very, very symmetric. Okay. Scores on standardized tests are typically symmetric. They try to design standardized tests to produce symmetric scores, distributions. This is left skewed. Left skewed is a little different. Some variables I could think of for left skewed, things that occur at like milestones. So like age at retirement, say, those tend to be left skewed because most people are retiring up here in these ages, maybe 55 and beyond. But there are occasionally people who retire much younger than that. They're just not as common. Age at a lot of milestones. Age of death would be very much left skewed. Most people are dying at older ages, but of course, rarely you do see people dying in middle ages and stuff like that, but not as common. Okay, so these are the different kind of distributions we'll probably mostly work with in this course. So the goal of the histogram and the goal of graphs in general is that there's three main characteristics or aspects of distributions that we're really trying to get at. And those three main things we're trying to get at are the center, like where's the middle, what's kind of the average or median. The variability, so variability means how spread out is the data? Is it all kind of condensed in one little area, or is it very much spread out? And then the shape, is it skewed, is it symmetric? And these three things together are the most important aspects or characteristics of a distribution that we're going to be really concerned with. And what we see with the histogram for quantitative data is the histogram is a really great way to start to see these types of things, the center, the variability, and the shape. In Chapter 3, what we're going to start talking about is, well, what if we don't just want graphs? What if we actually want some numerical ways to get at the center, variability, of shape? And that's what we will do in Chapter 3. So until then.